All right, today we're going to crack open a real classic. I'm talking about a problem from Irodov's famous book. We're looking at a cosmic body hurtling in from deep space on what looks like a collision course with our sun. Sounds dramatic, right? Well, it is. Okay, so let's get right into it. Put yourself in the shoes of an astronomer for a second. You spot something, an asteroid, a comet, something, and it's headed for the sun. You've got its speed, you know its general direction, but the big question is it going to hit, or is it going to just skim by? You see, this isn't just some dusty old math problem. It's a real physics puzzle, and our star is right in the crosshairs. So let's lay out the official problem straight from Irodov 1.210. We've got this cosmic body, and it's moving towards the sun. We know its initial speed, let's call it v0, when it's super far away. We also know something called the aiming parameter, which we'll call L. Think of it as how far off center it's aimed. Our whole mission here is to figure out the absolute closest it's going to get to the sun. Okay, this aiming parameter, L, this is super important, so let's make sure we get it. Imagine the asteroid is so far away its path is basically a straight line, right? L is just the distance from the center of the sun straight over to that path, a perfect perpendicular line. So if L was 0, bam, dead-on collision. The bigger L is, the wider the miss. You gotta understand, this one variable is the key to unlocking the whole problem. All right, before we jump in and just start throwing numbers around, let's think like a physicist. Any good physicist has a toolkit, and the first step is always picking the right tools for the job. You don't use a wrench to hammer a nail. And for this problem, this cosmic dance with gravity, we need two of the heavy hitters from our mechanics toolkit. And here are our two golden tickets. First up, conservation of angular momentum. Now, why does that work? Well, the sun's gravity pulls the asteroid straight towards its center. There's no sideways pull, no twist. And if there's no twisting force, no torque, then angular momentum has to stay the same. It's a lock. Our second tool, conservation of mechanical energy. Gravity is what we call a conservative force. It's not like friction, which bleeds energy away as heat. Gravity just stores and releases energy. So the total mechanical energy, that's kinetic plus potential, is also locked in. It's constant. These two laws are everything. Okay, let's put our first tool to work, conservation of angular momentum. The strategy is simple. We're going to look at two snapshots in time. Snapshot 1, way out in deep space, at the very beginning. Snapshot 2, the moment of truth, when it's at its closest point to the sun. So let's start with snapshot 1, when the body is basically infinitely far away. Calculating the angular momentum here is actually pretty simple. It's just its mass, m, times its initial speed, v0, times that aiming parameter, L. Remember, L is that perpendicular distance, so the calculation is nice and clean. Okay, now let's jump ahead to the main event, that moment of closest approach. This is the distance we're looking for, right? Let's call it r-min. Now, at this point, the body's velocity is going to be different, so we'll call that v-min. So the angular momentum at this exact instant, it's going to be the mass, m, times this new velocity, v-min, times our target distance, r-min. And here it is. This is the big aha moment of the whole problem. You gotta really picture this. When the asteroid is at its absolute closest point, just for that one single instant, its velocity vector is perfectly perpendicular to the line connecting it to the sun. Think about it. If it weren't, it would either still be getting closer or it would have already started moving away. At that turning point, the motion is perfectly sideways. And that, my friends, makes the math so much easier. No sines or cosines, just a straight-up product. So, since we know angular momentum is conserved, that means the amount it had at the beginning has to be exactly the same as the amount it has at its closest approach. We can just set our two formulas equal to each other. And look at that, the mass m is on both sides, so we can cancel it out. And boom, we have our first key equation, a really elegant little relationship connecting the start and the middle of its journey. Okay, tool number 1 did its job. Time to pull out tool number 2, conservation of mechanical energy. And we're going to use the exact same strategy. We'll look at the same two snapshots, far away and at the closest point, but this time we're going to look at them through the eyes of energy. All right, back to snapshot 1, way out in the void. It's so far from the sun that gravity's grip is basically 0. So by definition, we say its gravitational potential energy is 0. That makes things easy. All of the energy it has is motion energy, right? Just its kinetic energy, 1/2 mv0 squared. That's it. Now for snapshot 2. At the closest approach, it's a whole different story. It's still moving, of course, so it has kinetic energy based on that new velocity v-men, but now it's deep inside the sun's gravitational well, so we absolutely have to include its gravitational potential energy. And that's calculated with the standard formula, the one involving the gravitational constant gamma, the sun's mass, and our distance r-men. Whoa, hold on, we have to talk about this. This is probably the #1 mistake people make. That negative sign in the potential energy formula, it is crucial. Why is it there? Well, think of gravity as a well. To get out of the well, you have to add energy, you have to climb. So when you fall into the well, when you get closer to the sun, you're losing potential energy. It's going negative. It's like you're going into energy debt. So please, whatever you do, do not forget that negative sign. Okay, so just like before, energy is conserved. The total energy at the beginning equals the total energy at the closest point. And there you have it. Our second major equation is on the board. So let's take stock. We have two equations, one from angular momentum, one from energy. And we have two things we don't know, v-min and our prize, r-min. The physics part, it's officially done. Now it's just a matter of rolling up our sleeves and doing some algebra. All right, the stage is set. We've used our physics principles to build our two equations. Now it's time to solve this puzzle. The whole game now is to mash these two equations together and isolate that one variable we care about, r-men. So where do we start? Well, let's look at our two equations. The angular momentum one looks a lot simpler, right? Let's take that one and just rearrange it to solve for v-min. Easy enough. Now we have a neat little expression that tells us what v-min is, using all the stuff we already know. And, of course, our unknown r-min. And now for the magic trick. We're going to take that little expression for v-min we just made, and we're going to substitute it. Just drop it right into our big, messy energy equation. This is a classic move in physics and math. By doing this, we totally eliminate v-min from the picture. And what are we left with? One single equation where the only thing we don't know is r-min. We've cornered our variable. So now we just have to clean things up a bit. We'll do some algebra, multiply things out to get rid of the fractions, move all the terms to one side, and when the dust settles, you're going to see something amazing. This big, scary physics equation transforms into something you've seen a million times before, a standard quadratic equation. You've got an r-min squared term, an r-min term, and a constant, just like back in algebra class. And once you have a quadratic equation, you know exactly what to do, right? You pull out the good old quadratic formula. We plug in our a, b, and c terms, solve for r-min, and since we're talking about a distance, we obviously take the positive answer. And there it is, the final result. But hey, don't just write it down and move on. Look at it. Think about what it means. What if the asteroid is moving incredibly fast, if v0 is huge? Well, that v0 to the fourth power term becomes enormous, and the whole thing basically simplifies down to r-min being equal to L, which makes perfect sense. If it's going fast enough, gravity can't really bend its path, so it just flies by at its aiming distance. See, this isn't just an answer, it's a tool that predicts how the universe works. So, there we have it. We did it. We solved Irodov 1.210. But you know what? That final formula, that's not the real prize here. The most important thing we learned is the how. The strategy we used, the step-by-step process, that is the real physicist's mindset. That's the part you can take with you to solve the next problem. And here's that blueprint, broken down. This works for so many problems. Step 1, figure out what forces are involved. For us, it was just gravity. Step 2, based on those forces, ask yourself, what's being conserved? Is it energy, momentum, angular momentum? In our case, it was energy and angular momentum. Step 3, turn those conservation laws into actual equations, connecting a before state with an after state. And step 4, solve the system of equations you just created. That's the framework. That's the real lesson. So that leaves us with one last question to chew on. Our asteroid had enough speed to escape. It came in, swung around the sun, and shot back out into deep space, never to be seen again. Its path was a hyperbola. But what if it wasn't moving so fast? What if its initial speed, v0, was much, much smaller? Could gravity win? Could the sun actually capture it and pull it into a stable orbit, turning it into a new planet or moon? Well, that's a fantastic question and maybe something we can tackle next time.